everybody to our Eco Talks Friday seminar series. I have the distinguished pleasure of introducing my Eco Talks co-organizer, Megan Lickley. Megan is going to be talking to us today about her work involving sort of ozone depleting substances and very potent greenhouse gases. And then after talk, as a quick reminder, we have a social, but this Friday, it's going to be outside. It's not going to be upstairs. It's going to be directly outside of our seminar room today. So thank you so much for joining us today. Megan, please take it away.
Thank you. It's nice to see so many familiar faces from around town. Thanks everyone for coming. So I'm going to be talking today about my work evaluating progress on the Montreal Protocol. And I always like to start by with a figure of what we're observing in the atmosphere. So this is a figure of fluorofluorocarbon 11 concentrations in the atmosphere over time. And in this period of rapid growth in the early 80s, that's when CFCs were being used for applications like hairspray and refrigeration and foam blowing. And then around that time, we were also expanding our monitoring network of the ozone. We knew at the time the CFCs were depleting ozone in the stratosphere, but it was thought to be happening at a really slow rate. However, in 1985, the satellites flying over Antarctica measured severe depletions in stratospheric ozone in September. And so this is a figure here showing the total ozone abundance, the total column of ozone in the atmosphere, with Antarctica being at the center of that. And the hole really opens up in September. That's when it's really, really cold and when sunlight starts to arrive in Antarctica. So it gives sort of the perfect recipe for rapid ozone depletion when there's active chlorine in the stratosphere. Scientists rapidly rushed to Antarctica to do the work to verify some of these theories. And along with this growing hole in the ozone layer, there was rising concerns about what this meant for human health, especially when we're thinking about skin cancers and cataracts. So because of this gaping hole, this increased fear, and solid science, countries came together to sign the Montreal Protocol in 1987. It's still to this day the only UN treaty that's been ratified by all member states, I believe. And it led to some rapid cessation of production of ozone depleting substances. So for chlorofluorocarbons, those are CFCs. They destroy ozone because they have a chlorine atom on them. They were phased out in wealthy countries in 2000, phased out of production, and then in 2010, globally, they were phased out. And as a result, emissions of these gases have dramatically decreased, and we're starting to see concentrations of these gases depleting as well. Often, whenever I talk about my work on ozone, everyone says we're fine, right? And I think by and large, we've solved that problem. I think, we have made some impressive gains on solving this problem, but today we're going to talk about some of the challenges and ensuring that we maintain that progress. So I should add, before I get into the challenges, that one of the co-benefits of protecting the ozone layer was that these gases are very strong greenhouse gases. So pound for pound, they're thousands of times stronger than CO2 in terms of their ability to warm the atmosphere. This is a figure here by one of my colleagues, Gus Welders, that shows the relative contributions of CFCs to total greenhouse gas emissions weighted by CO2 equivalent warming. So the black line is the chlorofluorocarbon contributions to warming relative to that orange line, which is showing CO2 contributions to global warming. So in the 90s, about a third of total greenhouse gas emissions were coming from CFCs. Today, it's now just a few percent because of this remarkable treaty. These green sort of bands and blue bands here are showing what we anticipate the contributions would have been had there not been a Montreal Protocol. So had there not been some of these early treaties and the Montreal Protocol, we expect that these emissions would have continued to grow and our planet would be much warmer than it is today. So major success. But in 2018, this paper came out by Stephen Muska, who's a scientist at NOAA, and a number of his collaborators, that showed that the concentrations of CFC-11, so this initial figure that I showed you, have not been decreasing as quickly as we anticipated. So what you're seeing here is the blue and orange lines are showing measured concentrations in the atmosphere of chlorofluorocarbon 11. There's a few different CFCs. CFC-11 is one of the most abundantly produced CFCs. And what you're also seeing here is that there's been this departure from what we anticipated would occur in the atmosphere, which was these gray lines, what we previously projected would occur, and what we're measuring. So the gray lines are showing projections from International Scientific Assessments on ozone depletion that anticipated that the concentrations of these gases would decrease much more rapidly. So on the left it's from the 2002 assessment, and then line number 2 is from the 2010 assessment. And you can see our projections have continuously been sort of kicked down the road in terms of how quickly we thought we'd be recovering. So with this work came a lot of investigation on whether or not there were new emissions of these gases occurring that previously hadn't been occurring. But in this talk, I'm going to be talking about how we can assess what the underlying curve should be if we're fully complying with the Montreal Protocol. So what should we be observing in the atmosphere if we are no longer producing CFCs, and if we're following regulations for other gases that are regulated under the Montreal Protocol? One of the things that we're going to be talking about is this gap between what we project should occur and what we're observing. And then the other component of this analysis that they pointed out is that there's this increased gradient in the difference between what we're measuring in the northern hemisphere of these gases and the southern hemisphere. And that was used as a line of evidence that we have new emissions of these gases occurring. Does anybody want to guess why that might be a line of evidence? Students from my MSCSM class? Because we produce these gases largely where people live, and we more, in wealthier countries, and most of that is concentrated in the northern hemisphere. If we have an increase in production, we're going to start seeing a rise of concentrations first in the northern hemisphere where these gases are being emitted. So looking at this gradient is another line of evidence for understanding new emissions. Okay, so for the rest of the talk, I'm going to be talking about some of my work that goes into estimating this underlying curve, what we anticipate these underlying curves should be. And that means looking at what has previously been produced over time and continues to be a source of emissions. I'll define that in a little bit. We call them banks of old equipment of these gases, but also understanding how quickly these gases decay in the atmosphere. And this is a real source of uncertainty in understanding the global budget of these gases. And then third, I'm going to be talking a little bit about feedstock emissions of these gases. So currently, there are some permitted uses for the production of CFCs. I'll get into that in a little bit. They're allowed to be produced as feedstocks. And quantifying those emissions has been part of my focus over the last few years. And then the second part, I'll be talking a little bit about what the implications are of this work for ozone recovery and international assessments. So when I'm going to be talking about CFC banks going forward, this relates to the reservoir of these gases that's contained in old equipment that was produced prior to the phase out of production of CFCs. So CFCs contain an old equipment that can continue to be a source of emissions throughout the lifetime of the equipment. So even if we no longer are producing new gases, we're no longer chemically manufacturing new gases, we can still expect there to be emissions of these potent greenhouse gases from older equipment that was produced prior to the regulations, the enforcement of the regulation. Banks can be released quickly. They can have short lifetimes. So for uses like aerosols, they're usually produced and emitted within 1 to 2 years of chemical manufacturing. For uses like refrigeration or air conditioning, the lifetime can be closer to 10 or 20 years. There's a lot of uncertainty in that. And then for other uses like foams, the lifetimes of those guys, you expect that to leak out at 2 to 3, 4% per year. So they have longer lifetimes, the banks of these gases. And you know, there's a range of CFCs that have been used. The most abundantly produced ones were CFC 11 and 12, so these ones on the left. Those were used for refrigeration, closed cell foams, refrigeration, aerosols, open cell foams. CFC 113 has been used as a solvent. And then 114 and 115 have been used as aerosols and propellants and heat pumps. And then the more minor ones, CFC 113, 114, and 115, they're currently still being produced to create other gases. So they're used as a feedstock, or they're emitted as a byproduct, in creating some of the new newer generation of coolants, which are HFCs. They don't have chlorine. Okay, so why am I interested in quantifying these historical, the banks of these gases? Well, one of the reasons is that when you look at previously published estimates of how much is still out there in old equipment, the estimates vary quite widely. This is the 2003 International Ozone Assessment anticipate there'd be almost no banks remaining for CFC 11. But they've had to update their estimates when they realized there are errors in that. The IPCC has provided estimates as well. And one of the reasons why there's such a wide range of estimates is because there's different ways and assumptions that are being made in computing those estimates. So one of the ways of quantifying banks has been to estimate them using a top-down method. So when you use a top-down method to quantify banks, you look at the cumulative difference of how much has been produced over time. So you can add up historically how much has been produced. There have been records, there have been reports of this, both at the industry level and to the and reported to the UN. And you can take the sum total of how much has been produced, and then subtract off how much has been emitted. You can estimate emissions using concentrations of these gases, year-to-year changes in concentrations of these gases in the atmosphere. So this is what we call the top-down estimate of bank, and it's an accurate formula so long as you know how much has been produced and emitted, but it's very sensitive to small biases in either of these values. If you're taking the cumulative sum and that can add up to a large bias over time. But this has been sort of the traditional approach for quantifying banks in the international scientific assessments of ozone depletion from 2006 to 2018. Do my MSCSM students want to guess what the other method for calculating banks, quantifying banks might be? Other than the top-down? The bottom-up method. So just to show you, so the small biases can propagate into large uncertainties and bank estimates over time. So this figure on the right is showing how lifetime uncertainties, so reasonable estimates of lifetimes of these gases in the atmosphere that have been previously published. Our best estimates of these range for CFC 11 range from 45 years in the atmosphere to 63 years. So depending on what lifetime you use, depending on what you assume your production to be, you take what's been reported versus assume there's been underreporting, or you can get very large differences in bank estimates. Using the bottom-up method of calculating banks is what the industry folks typically use, and this is a bottom-up tallying method. So you would start in your first time period and calculate how much has been produced, subtract off that how much is directly emitted into the atmosphere, and then iteratively calculate how large the banks are over time by assuming a certain leakage rate out of banks. So using this method, if you knew how the release rates from banks, if you knew how much is directly emitted and when you're chemically manufacturing or filling equipment, you knew how much was being produced over time, you could accurately simulate bank sizes over time. But one of the limitations of this approach is that it doesn't make use of observed concentrations in the atmosphere, and it relies on industry and country reported data. So what I've been doing in my analysis has been trying to merge as much information as we can together, rather than taking approaches separately. Often in the literature, you see bottom-up methods used and top-down methods used to try to check bottom-up methods. You can do that separately, or you can take some apply some computational methods to merge assumptions from both of these approaches together. So I've been asking the question: if can we better constrain all the uncertainties in these processes if we start jointly modeling industrial and atmospheric processes together? So that's one paper I'll quickly touch on some results on. And then building on that method, can we constrain uncertainties even further if we start jointly modeling multiple gases, both industrial and atmospheric processes together? And then can we take that even further if we jointly model the industrial processes that some of these gases are correlated through? So in terms of the industrial and atmospheric processes, I've used a method called Bayesian parameter estimation, where we take information from the bottom-up approach. We simulate banks over time using estimated production values and leakage rates, and then use the same parameters to estimate emissions over time. However, all of these input parameters are very uncertain, and so we account for that in our bottom-up simulation model. You can then jointly simulate, take your emissions estimate over time, and with that, estimate what you would see in the atmosphere. So we don't observe emissions, we observe concentrations in the atmosphere, but you can infer what those concentrations would be if you have emissions estimates over time. So in order to infer concentrations, you need to have an estimate of your emission and an estimate of how quickly your gases decay in the atmosphere, your atmospheric lifetime. So in order to apply Bayesian parameter estimation, we use a method called sampling importance resampling, where all of the input parameters, we make informed estimates of what their prior distributions would be. We sample from those prior distributions, we simulate our three equations here, and then we compare our observations. We compare our simulated concentrations of these gases, what's in that green box at the bottom there. We compare that with what's been observed in the atmosphere and use observations to constrain our parameter space. So all of the sets of parameters that are closer to our observations would be kept in our posterior estimates. All of our combinations of parameters that are really far from observations would essentially be thrown out, and we end up with a posterior probability distribution that's both consistent with what's been the simulation model from what industry uses, and is also consistent with what we're observing in the atmosphere. One of the things we've done in this work is that instead of looking at each gas independently, we've started building in information that applies across gases. So to estimate the lifetimes of gases, we've used information from chemistry climate models. This is a simulation here, or these are model simulated atmospheric lifetimes of CFC11 on the left and 12. And what I want you to take away here is that if a model estimates that the atmospheric lifetime, well, first that you can see the models have variation in what they model the atmospheric lifetime to be for both of those gases. They start high and converge to a steady state towards the end of the time series. But also that if a model estimates lifetimes to be low for CFC11, it will also estimate lifetimes to be low for CFC12. So we account for this correlation exhibited by chemistry climate models in our modeling approach. And one of the reasons why it makes sense to do this is that while we're really uncertain about the lifetimes of CFC11 and CFC12, we can start constraining that uncertainty by accounting for the fact that what governs their lifetimes jointly governs their lifetimes. And so what I mean by that is that CFCs, their loss in the atmosphere, so their loss process, what governs their lifetimes, is how quickly they make it into their loss region. So this is a figure here showing, do I have a pointer? Showing on the x-axis the latitude, our globe, like laid out by latitude, by the South Pole is on the left and the North Pole is on the right. And then the y-axis here is pressure coordinates, so moving up into the atmosphere. And CFCs are produced at ground level where we have our industries, and they're fairly stable in the troposphere. This is one of the reasons why we were so enthusiastic about CFCs earlier in the 20th century. They were pretty inert gases, relatively unharmful. But once they make it up into the stratosphere, higher up in the atmosphere, they start breaking apart. So through interactions with UV radiation. So this is a process called photolysis. And as UV radiation interacts with these molecules, they cleave off their chlorine. And that process allows the chlorine to start reacting with ozone and depleting ozone. So their loss process is governed by how quickly CFCs make it into their loss region through transport between the troposphere and the stratosphere, where the ozone layer lies. And this transport process is what's the most uncertain in that loss process, but it jointly governs the lifetime of CFC 11 and 12 and other CFCs. So we're uncertain about their lifetimes, but we know that the reason that we're uncertain is because of processes that are similar to both of these gases. So we account for that in our modeling process. And then after considering all of these uncertainties and how quickly these gases are released, how much has been produced over time, and how long these gases live in the atmosphere, we have a whole range of estimates of what our abundances of CFC11 in the atmosphere would be. And that's our prior estimate, which is shown here in gray. And then we compare, as I said before, we compare all of our simulated mole fractions or constitutions with what we're observing in the atmosphere. That's what's blue. And we keep in our posterior the simulated values or the simulated time series that are closest to what we're observing. And that's shown in red. So all of our input parameters can be constrained using Bayesian parameter estimation in this way. And so I'm going to show you some of the results of how other parameters have been updated over time and what this can tell us. First is that our estimated bank values are highly uncertain still, but that our best estimate of banks, which are shown here in blue, are larger than what's been previously published by the international assessments. This is true for both CFC 11 and 12, and for a suite of ozone depleting substances that I've subsequently evaluated. So they're currently large enough to delay ozone recovery by about 6 years and contribute 9 billion metric tons of CO2 equivalent emissions, but then they're highly uncertain still. One of the reasons why we found them to be much larger than previously estimated is that previous estimates assumed what was reported was accurate. There has been evidence that what's been historically reported has been underestimated by as much as 20%. Russia was not reporting their production for a number of years in the 80s. They were producing about 20% of the global supply chain. So I don't think it's unreasonable that our estimates are much higher than what's been previously produced. But that it's so far with our methods, we still have a lot of uncertainty in what's out there. And that means that we're going to have a lot of uncertainty in terms of what future emissions will continue to look like. We also found that our atmospheric lifetime, we were able to constrain atmospheric lifetimes of our gases more than what the best current recommended atmospheric lifetime ranges have been. So our prior lifetimes, our range is shown in gray here, and our posterior is shown in red once we've updated it in our model. And then on the right is in the black arrow is what the current recommended range of lifetimes are. So our posterior lifetime estimates for all three CFCs, CFC 11, 12, and 113 that we studied together, they're all shorter than recommended values. Okay, so what are the implications of this? If lifetimes are actually shorter than atmospheric values, then that means that observationally inferred emissions have actually been reported, have been biased low. So the lifetimes that have been used to infer emissions have been too high, meaning they've been underestimating total global emissions to date, if our values are correct. And then a final finding from this joint modeling work is that modern day emissions, so if you think of 2010 onwards, cannot be explained from bank emissions alone. So this is showing in the top corners of each of these figures is showing for three different CFCs, CFC 11, 12, and 113, our estimated emissions, posterior estimated emissions from new production instead of this is the non-bank emissions part of our simulation model. So CFC 11, this confirms what's already been published on CFC 11 having a new unexpected emission source, but it was the first paper to find a new emission source of CFC 12, and we also found the CFC 113 emissions were much higher than expected, about 10 times higher than what was expected to be coming from the known sources of its use as a feedstock. So non-bank emissions of CFC 113 is still permitted to be used as a feedstock, but its emissions are much higher than expected. So those are some of the results. I'm happy to say that this unexpected emission of CFC 11 has since declined since the 2018 finding of its new source. And I'm also happy to say that the reference point is no longer the previous international assessments, but they've used my modeled estimate and their new reference of what we should expect in the atmosphere. So this is the same group, Steve Mosca and Noah, published findings that his work led to a huge investigation, and Eastern China had been a new source of CFC 11. It shut down its facilities, and these emissions have declined, in large part because of the work of him and his colleagues and a number of other scientists in the field. Okay, so CFC 11, that's story closed for now. But these gases are continuing to be a source. The replacement chemicals of these gases are now the focus of my work. And as CFCs have been phased out, they've been replaced by other gases that don't destroy ozone to the same degree. So HCFCs were the first replacements, the suite of replacement chemicals. They still have a chlorine atom, hydrochlorofluorocarbons. And so they did deplete ozone a small amount compared to CFCs, but they've since been replaced by HFCs, hydrofluorocarbons, and those do not contain chlorine. But all three suites of chemicals are all potent greenhouse gases. And producing these new suite of chemicals still requires chlorofluorocarbon or hydrochlorofluorocarbon production. So if you look at the 2022 ozone assessment, in chapter 7, I've looked at this figure 1,000 times over the last 3 years. They have this network of production of the gases that are currently in use. So HFCs are the end product that we currently are using in much of our refrigeration and cooling systems. And in order to get an HFC produced at a plant, you have to have a series of chemical reactions to get there. And so often you start with something like carbon tetrachloride, so that CCl4, the blue box on the left, and then you go through a series of chemical reactions to get to your end product, HFCs. So I'm going to be focusing a little bit on some work that my previous postdoc, Stephen Bourget, published in Nature Communications in 2024. where he looked at a small section of this pipeline, particularly the part that was looking at CFC, the CFC production. So CFC 113, here again, CFC 113 in the middle is produced in order to get one of the HFCs, and so are a couple other CFCs. And what we were noting was that if you look at the emissions of these gases, they too have not been decreasing as quickly as we anticipated. And so the amount that's been produced or reportedly produced as a feedstock for these gases has been decreasing over time, but we're not observing that trend in the atmosphere to be decreasing at the rate that we would expect given what's been reported. So he looked at a small section of this pipeline, the part that has CFCs, but also some HCFCs. And so what you're seeing here is there are some CFCs and HCFCs that are intentionally produced. And there are some, the little dashed arrows at the top for CFC 114 and 115. Those are unintentionally produced as a byproduct. It was a thought when parties to the Montreal Protocol first approved the use of CFCs as a feedstock, it was thought that their leakage rate would be very small, 1%, 0.5%, and so it was permitted. They were permitted to be used as a feedstock. But through Stephen's work and through a range of other work from other scientists, we've since seen that this rate is much likely to be almost an order of magnitude higher than what was previously estimated. So what Stephen did in this work was he built the same sort of simulation model out to have to be modeling the production of these gases as a function of their end product. So we have an estimate of how much HFCs have been produced over time. This has been reported to the UN. If we take that estimate and then break it down by this pipeline and simulate the chemical manufacturing process by tracking the number of fluorine atoms through this chain of reactions, we can start using the same sort of technique to constrain how much has been produced of these feedstocks and how leaky this feedstock pipeline must be. And in doing so, he found that you can use observations. They're not all unique to this pipeline, but some of these gases were perfectly positioned to be unique to this pipeline, specifically HCFC 133A. So by jointly modeling this whole pipeline and using observations of these gases to constrain each of these different pipelines, we found a few things. And one is that the CFC pipeline is likely leakier and being used more than what's been reported. So our estimates were that what's been reported in non-A5 countries, so wealthier countries, of these gases is in line with what our model suggests, but that there may be uses of this feedstock pipeline being used, the CFC pipeline being used and not reported in developed or lower income countries. Which may, or depending on the facility, this may or may not be in line with current regulations. And the other thing that he showed was where we would be today if we were not permitted to use CFCs in this manufacturing process. And so today we have concentrations of CFC 113 that are about 70 parts per trillion in the atmosphere, and that's shown in the dashed line at the top here. If we did not have this pipeline of gases used today to create HFCs, we would likely be about 5 ppt lower today. That's a lot more dramatic if you start looking at 115 or HCFC 133A. We would not be observing HCFC 133A today if it weren't for this leaky feedstock pipeline. Okay, how am I doing on time? 336. Okay, so moving on to what this actually means for the ozone layer. In more recent work, in collaboration with a few different authors of the ozone assessments, we looked at the projections of ozone recovery for each of the last 5 scientific assessments of ozone depletion. And in part of these assessments, they produce an estimate when ozone will recover back to 1980 levels. So they look at how abundant ozone depleting substances are in the atmosphere. They use estimates of, they project forward how abundant they anticipate them to be given our current best estimates of banks, lifetimes, and assuming compliance with current controls. And then they create this metric or estimate this metric called equivalent effective stratospheric chlorine. So this is a metric that aggregates all ozone depleting substances together to estimate the amount of active halogens in the stratosphere. So the active amount of chlorine or bromine in the stratosphere that's attracting and destroying ozone layer. So EESC is not a measure of ozone destruction, but it's a proxy for ozone destruction based on what we are measuring at the abundances of ozone depleting substances at the surface. And what we found in our assessment, which was published in Atmospheric Chemistry and Physics, is that up until the last assessment, so up until 2022, most assessments had predicted that the equivalent effective stratospheric chlorine return date to 1980 level chlorine would be occurring around 2040s. So the reason why this is sort of an important metric is 1980 is sort of seen as the time before the ozone hole was detected. This time pre-ozone depletion. It's not exactly an accurate year to use, but that's always been a benchmark when we'll be back to 1980 levels. That's sort of what we're aiming for, to be back to 1980 levels of chlorine. So it was always anticipated, each of these assessments, 2006 up to 2018, estimated to be back to 1980 levels by 2050, between 2045 and 2050. And then the 2022 assessment came out, and it anticipated a 17-year delay from all previous assessments, that we would actually be returning to 1980 levels in 2066. So 17 years later. So what went on in between these assessments? So the first thing is that the metric for calculating EESC changed, and if you over time, and that sort of disguised that we're not actually at a dramatic departure in 2022, but there's actually been a consistent sort of delay in recovery expected over time, as this metric has been sort of iteratively updated in time, and it's sort of just disguised or hidden that this is sort of slow kicking the can down the road in ozone recovery. And then we looked more deeply at all of the different sort of combined factors and that's going into our projections of ozone recovery. And so you could think of changes in our projections of ozone recovery rely on our atmospheric lifetimes. Those have changed between assessments. So atmospheric lifetime estimates have gotten longer, and that has led to an expected delay in recovery. Our bank estimates, well, I was involved in the 2022 assessment, and I produced much larger bank than all previous assessments. And so that has been part of the story of why we've delayed, had a delay in ozone recovery of a few years. But then there's also this feedstock chemical, carbon tetrachloride, that has also been sort of a mystery gas that has led to a large delay in recovery. So back in 2006, all of these things we did not really anticipate. We didn't anticipate that lifetimes would change, that we'd have larger banks than previous, and that carbon tetrachloride would continue to be produced and emitted at such large quantities. But today, in looking back, we can see these updates, and that gets us all the way there. So what I'm showing here, just to be clear, is in 2006, our initial return to 1980 levels of chlorine were about 2047. Then we updated that using the current method for calculating EESC, and that gets us to the end of the empty arrow, the white arrow. And then for all of the updates back to up to 2022 levels, updating it the lifetimes banks and carbon tetrachloride, which is the purple arrow, that gets us up to 2026. So we find that banks is part of the story for why we've delayed ozone recovery. It's not all of the story. Part of it is updates in science that constrain lifetimes. And then part of it is that other gases that are still produced were not previously anticipated to be part of the story still, like carbon tetrachloride. Okay, so before I end, I will skip through the carbon tetrachloride updates over time and talk very briefly about where this work is heading, and that as one of the nice parts about the Montreal Protocol has been that it's a treaty that's been iteratively updated over time to reflect new science and reflect new industrial practices. And one of the newer amendments to the Montreal Protocol came in 2016 called the Kigali Amendment. And the Kigali Amendment regulates the newest suite of halogenated gases, so hydrofluorocarbons. Now, the nice part about the Kigali Amendment is that even though HFCs don't destroy ozone, they were included in this amendment because they're a potent greenhouse gas and they have been used as a replacement chemicals to ozone depleting substances. So I've shown you a lot of the work where there's a lot of uncertainties in our estimates of banks and lifetimes of these gases and of production processes. One of the questions we want to ask in my group was, how much will these uncertainties of all of these factors limit our ability to detect future breaches in the Kigali Amendment? So for CFC-11, when there was that breach in emissions, it took about 6 years of data before publication of the results. We wanted to know how long it would take before we could confidently say there was a new breach in the amendment. So this is work that's ongoing. It's been taken over by my new postdoc, Matthew Wozniak. And some of the results of this work that we're going to be submitting soon are that depending on the quantity of production, it could go undetected. We are running a range of analyses, but if countries continue to produce at a 25% above compliance, 80% we have an 80% chance of detecting that, 20% chance of not detecting it. If it's closer to 15% above compliance levels, then we're likely not to detect it. We're still refining that number, but we're in about that range, that we're likely not going to detect breaches of a certain magnitude, 15 to 20% above compliance with our current understanding of the atmosphere. If it's an abrupt breach far down the road, then it's a lot more likely that we'll be able to detect it. So what do we do given all this uncertainty? We can continue to work on atmospheric lifetimes of these gases, but I would say lifetimes are key to inferring global emissions and future concentrations, and so it's going to continue to be a source of work in my lab. Banks have also been important for the recovery of the ozone layer. For CFCs, they're expected to contribute to a 6-year delay, but for the suite of ozone depleting substances, it's about an 11-year delay that banks alone are going to provide in the future. So there is some policy opportunity for recovering banks and preventing these future emissions from occurring. We continue to find that reported production values of all ozone depleting substances are highly uncertain. I didn't get to the CCL4 budget, but I'll skip over that and say that the HFC phase down, so the new Kigali Amendment, remains difficult to monitor, which brings me to the last point that I just wanted to put a little bit of a plug in for the new grant that we're working on, funded by the Quadrature Climate Foundation, which is to expand our flask monitoring network of HFCs globally. Right now, there's a network of HFCs of measurements of these gases that's shown in red and blue here. And you can see that what this is showing is our current measurement network. So NOAA measures a lot of these gases in the US. There's another network called A-Gauge that monitors these gases in some locations outside of the US as well. And with the current monitoring network, we're able to infer gases fairly well over Europe and North America and parts of East Asia. There's a little monitoring network in Southern Australia, but much of the rest of the world remains unmonitored. So one of the goals of this grant is to expand our monitoring network to these under-monitored, under-sampled regions in order to add new constraints to ongoing HFC emissions of these gases. Okay, I will end there. And and this is the team of people working on it. So we have a great team here at Georgetown. Matt Wozniak, Philip Wolf, and Emily Siegel just joined us to work on this project, and Taylor Jones is also involved. We're also collaborating with folks at NOAA, Steve Motska, and Isaac Viment. And then MIT, at MIT, there's Luke Western who's involved in this grant, and we're also working with colleagues at the University of Bristol, and we're currently working out 5 to 10 new partnerships in undersampled regions, and we're open to suggestions if anyone has partners in these undersampled regions that may want to get involved. Well, that I'll thank my collaborators and my funders, and thank you all for being here today at the end of a long week. Do you take any questions?
Rebecca? Yeah, thank you. So thinking about these new regions, what kinds of parameters are you optimizing for where you want to take samples? Like, is it in dense urban areas, or is it in the middle of nowhere? Like, what is it really important for you to know about where these CFCs are? HFCs.
Yeah, so HFCs right now they're largely being produced in South Asia. That's a big production region. So being in proximity to where they're being produced and then consumed, and they're being consumed in high-income countries and hot countries largely. Being in proximity to these locations can help constrain our global budget of these gases. You don't want to be in the middle of the city. That makes it really difficult to decipher where the emissions are coming from. You'd rather be in a more remote location so you can start mapping. Like if you look at this map, you can get sort of a large footprint from any one station if you're somewhat remote. So mountain ranges are really difficult to model. So there are other you want to be in a place that's accessible but remote and not a mountain range and not in the middle of the ocean. So there's a lot of, and you also want to have, people there. I mean, one of the biggest factors we're finding is that you really want to have engaged partners who are going to show up every week to take these samples and be willing to troubleshoot along the way. So it's been a fun challenge for us to try to find these people in the right location. Cool. Okay, thank you. Taylor, did you have a question?
Yeah. So with the return to 1980 levels being delayed, 6 years, 11 years, or however long. I know at the height of the ozone hole problem, there were huge public health worries, right? Skin cancer, crop health, very scary things. With things the level they're at now and that return getting delayed, are there still lingering public health concerns from the depleted levels?
Yeah, so ozone depletion reached its peak around year 2000, and it's debatable whether or not we've significantly improved since then. So the trend, because if you're looking at total ozone levels, and then reaching a low point in 2000, that trend upwards to ozone recovery is significant some years and not significant other years. So we're still at a pretty low point in total ozone. So wear your hats and your sunscreen and sunglasses. But I think people have been working on this for a long time, have good reasons to think that we're still recovering, even if it's not as rapid as we anticipated. A lot of the sort of year-to-year delays come from contributions from climate change, actually, like wildfires that accelerate ozone depletion. So things that aren't necessarily related with ozone depleting substances themselves, but accelerate the chemistry in the atmosphere, in the stratosphere for ozone depletion.
That sort of dovetails nicely with my question, where I was wondering if there are events related to climate change that may make that bank of CFCs, et cetera, more vulnerable to emissions, like hurricanes ripping through particular industries or areas.
Not something I have seen papers on. I imagine like earthquakes would lead to a large emission source. But I couldn't tell you how big it is, but I don't, on a global scale, it probably would be indistinguishable. But I think that's a good point. Yeah.
Follow up to that, how well do we know where the production facilities are for these chemicals?
I think they are documented, and it's not information I have the coordinates from, but some of my colleagues have it. I don't know how complete, whether or not that's a complete list, I think is a big open question, especially when we don't have monitoring sites in places that maybe are less willing to share information.
There's 2 questions online.
Oh, okay.
I think Brian and Colin.
Okay. Oh, Colin.
Hi, yeah, I mean, I think Gabby may have just asked my question. I mean, how well do we understand the geolocated basis, the facilities that are producing these? And can we infer anything about their operations using remote sensing tools?
Yeah, that's a question that Taylor and I most of the time.
Shocked to hear that Taylor's thinking about that.
Hi, Colin.
Hi.
One of the challenge, I mean, so, remote sensing tools have been useful for methane, but these are gases that are occurring in parts per trillion, so much less methane is more like parts per billion. So these are much less abundant in the atmosphere. I think for most of these gases, they don't have as a unique signature that you can measure from space, but it's part of our a project that Taylor is going to tell you the answer to in 6 months.
Super, thanks.
Brian had a question too.
Oh, okay, Brian, is he there or is it a text?
It was in the chat.
I'm both here and in the chat. Can you hear me? Am I the voice from above? Thanks, Megan. That was an awesome talk. I'm wondering, I know very little about the timeline between when these substances are emitted or produced and when they reach the atmosphere. Are there any sorts of nature-based solutions that can be really effective in sort of stopping them from actually reaching the atmosphere?
There are solutions, but I wouldn't call them nature-based to my knowledge. I mean, so like the ocean is a sink for these gases. Some of these gases, a very small fraction of the total emitted gases end up in the ocean. And some of them break apart in the ocean and some of them resurface 50 years later. I wouldn't call that a nature-based solution. I think the best solution right now is more or less like incineration of these gases. You can destroy them pretty easily if you incinerate them. And there are some efforts to do that. But because they're so widespread in equipment, our cars, our refrigerators, personal uses, so many personal uses, it requires a really coordinated effort to capture them before they're released. So without some large incentives to do so, or a large coordinated effort, it would be a total small fraction of the pie. We'll start with the student and then I'll ask you. Yeah.
Why are there more CXCs replacements in developing countries? They have less policies or something to do with their industry?
I mean, I think it's an opportunity for growth for these countries. It's a good industry to be in. And I think DuPont was a big producer of these gases in the US and was actually a big champion for phasing out CFCs globally. And I think they have a more diverse, well, I don't know the answer to this, I should just say. But DuPont has a diverse set of chemicals that they produce, and so I don't think they're as profitable for relative to other chemicals that are being made. But that's a good question. Other than the economic opportunities, it might be cheaper to produce them in lower income countries right now, and these countries are growing rapidly. That would be my best guess. Pete?
So I think I've asked you this before, but I'm just amazed that you could sample like a single site in South America on the ground for HFCs, and that could somehow capture variation in HFCs, both in a sort of latitudinal and longitudinal and altitudinal way.
I may be overselling this. That would not be like how I would describe. Yeah. So in order to get a good sense of where emissions are coming from, you probably need to sample at least, well, we're starting to sample at least once every other day. So once a week you couldn't map it with one single sample. And the vertical profile is not something we could do know very
So
well.
there could be
these
enormous
gases.
variation.
Yeah, and so, yeah, one of the things that remote sensing does do well is there are some satellites that can measure stratospheric abundances of these gases quite well. It's different when you look through the stratosphere at the sun. You can capture the signal much better than if you're looking down at the Earth. So getting like sort of the distribution of these gases, you can use data to get the distribution of these gases that way. On the ground samples wouldn't tell you a lot about what's happening up in the atmosphere. It can be coupled with atmospheric transport models to tell you where that air parcel was previously. And so through a lot of statistics and atmospheric modeling, you can sort of run a back trajectory and get a sense of where all those samples, where the most likely emission source must have been to give you what you're measuring on the ground. Taylor does a lot more of that than I don't do any of that. Taylor does that kind of work. Yeah, and
Yeah, I'm not familiar with the details of the Montreal Protocol, but I do wonder if, given all the uncertainty around quantifying emissions, if you have any concerns that requirements of the Montreal Protocol are inadequate to deal with the problem. In other words, do required measures necessarily depend on accurate emission quantification or not? Is that, I'm not sure if I'm.
I think there's a lot of
you worried about policy around measures to deal with these emissions, given all the uncertainty. And
so there are policies, some policies in place to deal with some of these emissions that have been more effective than others. Like byproduct emissions when you're in the manufacturing pipeline. I think what I would really like to see is increased transparency from industry on what they're producing when. So there's a lot of reporting at aggregate levels of what a country, like how many HFCs on aggregate has been produced, but that's not each year, but that's not disaggregated by HFC. We don't measure the aggregate. It's really difficult to tell what's happening when you say this many tons of HFCs produced. So more sort of discretized information, I think, would be much more helpful. Industry is very secretive about which pipeline they're using, which feedstock pipeline they're using. But I don't know. I mean, I'm an industry person, so I don't really understand how important all of that is. But having, I think, more transparency would allow us to make better inferences with the data that we do have, or make more accurate inferences with the data we do have. Yes.
Hello. I'm curious about the overall other chemicals that would deplete the ozone layer as well, such as you mentioned about the CCl4. It is also found in like products like emission. It's also emitted through products like aerosol. Do we have like a ranking of like how difficult it's to prevent these other like the CFC, HCFC, and such as like CCl4 to emit through and deplete the ozone layer? Is it going to be a difficulty or like the easiness for them to deplete?
No, yeah, okay, so there's a metric. So just like with greenhouse gases, we can sort of compare them based on how potent they are at warming the atmosphere. We call it the global warming potential of a specific greenhouse gas. There's an ozone depleting potential metric as well that gives you this estimate. So looking pound per pound of carbon tetrachloride versus CFC11, you can compare their ozone depleting potential. I think carbon tetrachloride is a more potent ozone depleting substance, and I always forget the numbers. But the ozone assessment, which is on NOAA's website, in their appendix, they have all the ozone depleting potentials of each gas, and that ranks how efficient each gas is at destroying ozone relative to CFC11. So it gives you a comparison to, like, CFC11 is kind of the CO2 of ozone. It's what everything's compared to.
Does my colleague follow up? As in, is it possible to replace some chemicals that contain to like them in like a lower potential chemicals instead?
Yeah, so this is what happened. So some of the amendments to the Montreal Protocol replace CFCs with less ozone depleting potentials. But there's been some, in hindsight, we may have done it more rapidly than necessary. So HCFCs don't destroy ozone as much, but they still destroy ozone. And then those were replaced by HFCs, which don't deplete the ozone layer. HFCs are stronger greenhouse gases than HCFCs. So we went really quickly to HFCs. Maybe we would be better off if we didn't. And since we're kind of weighing these two different environmental harms against each other.